Okay, so we're going to talk about flywheels. Now, what is a flywheel? Um, Actually, a flywheel is a mechanical device that stores energy, right? Or we have a huge mass, or there's some mass that due to its inertia, um, it um, basically helps us to smoothen the operation of engines or such systems that produce power, and that power fluctuates, right? So if we consider this figure over here and look at this figure, let's say that the power input or the torque input is Ti, and the with in angular displacement of theta I, the output um, torque is T naught with the angular displacement at the output theta naught. And let's say that we have this mass that has inertia I and theta, right? So now let's see if we want to write the equation of motion for the above system. So that is going to look like this, that the sum of the um, the equation of motion would look like that Ti, right, which is a function of the displacement and the velocity at the input, minus the torque output, which is a function of theta naught and theta naught, theta dot naught, minus I theta double dot of the flywheel, right? And that should be equal to 0. So the sum of all of these should be equal to 0. Now, um, we can rearrange this equation, and that would look like I theta double dot on one side, and that will be equal to theta Ti minus T naught on the other side. And since let's consider that this is rigid, um, um, therefore my theta I is equal to theta, and it is the so and also your my omega I is equal to omega. Therefore I theta double dot is equal to Ti theta of omega and minus T naught theta omega, a function of these, right? So hypothetically, if we look at a flywheel, let's consider this figure that we have um, the turning moment. I would say, let's say that on this axis, we have T and omega, and over here it is the angular displacement or the rotation of the crank of, let's suppose that it is an engine. So let's consider the initial velocity, um, and the torque over here, and let's say that that is omega 1, right? And it stays omega 1 until there is a power stroke, let's say, and that power stroke starts at some theta 1, and it terminates at theta 2, rising this velocity to another level, which is omega 2, right? So that goes to omega 2 during the power stroke. And the energy that is supplied in this power stroke can be calculated, or it can be determined by the area of this rectangle, which is, let's say, U1, right? So this is the amount of energy, and that will be equal to t times the difference between these, or t times the length of this side of the rectangle, which is theta 2 minus theta 1. So it will be Ti times theta 2 minus theta 1. Now let's say that the velocity that we have right now, that is omega 2 at this position, and let's say that it remains again remains, or somewhat it is omega 3. We can also, if there is no change, it's still omega 2, but let's assume that we have that equal to omega 3. Now at this omega 3 we have some power output from the system, right? Or power is spent over here. So that starts at an angle theta 3, and or the power that is consumed, or the energy that is consumed, is between theta 4 and theta 3. So now, since this is energy that is consumed, so it is going to be, if we call this positive, then this should be negative, and the amount of energy that is spent, which brought the velocity of the system from omega 3 to another level, omega 4, is given by the area of this rectangle, and the area of this rectangle is going to be equal to T naught, but I would call this U naught, right? The energy output is T naught times theta 4 minus theta 3, right? In this case, it was ui, and that was equal to ti times theta 2 minus theta 1, right? So now this is the situation. Now we can have three different scenarios over here. Okay, if omega 1 is well, I would say, if omega 4, which is the energy, which is the velocity at the end, is equal to omega 1, that means that the energy input to the system and the energy output from the system is the same. But if omega 4 is greater than omega 1, this means that more energy is supplied into the system, and there is less energy output from the system. So therefore the velocity of the velocity increases. Now we can have another scenario in which omega 4 is less than omega 1. So that would mean that the amount of energy that is the input to the system is less than the output of the system. Therefore, the final velocity is less than the initial velocity of the system. So these can be three different scenarios. And let's say if we talk about the about a system where the energy changes, or there is fluctuation of energy, or there is variation in energy. Let's say that the initial energy is E1, and that is the kinetic energy, which is equal to half I omega 1 square. And let's say that that went into another level, which is E2, and that is half I omega 2 square. So that is going to be the kinetic energy. Now the difference between these two energies, or we can rather say delta E, is equal to E2 minus E1, which is equal to half I omega 2 square minus omega 1 square. So that is going to be the difference between these two energies. And this is the engine torque for one cylinder, that is shown over here, where this is the energy, as I said, the energy input, right? And this is the energy output that at different angles of the crank. Now, uh, there are two different quantities that we define here, and those are the CS. CS is the coefficient of speed fluctuation. Now, what is the coefficient of speed fluctuation? This is omega 2 minus omega 1 divided by omega. So we call this the coefficient of speed fluctuation, and you probably have heard about it in theory of machine. If not, then CS is equal to omega 2 minus omega 1 over omega. And what is omega? Omega is basically the mean or the average of the two speeds, which is omega 2 plus omega 1 divided by 2. So basically it gives you the mean velocity of the system, right? Now, in order to look at this, let's say that there is this delta E, which is equal to E2 minus E1, and that is half I omega 2 square minus omega 1 square. Now let's write this in another way. I can say that it is half I, and I can factorize this, which is omega 2 square plus omega 1, sorry, omega 2 uh, okay. So I can write that omega 2 minus omega 1 into omega 2 plus omega 1, right? So I can write this in this form. Now, since my CS is equal to omega 1 plus omega 2 divided by omega, if you look over here, omega 2 minus omega 1, sorry, uh, the coefficient of speed fluctuation is omega 2 minus omega 1 divided by omega, right? So I can say that omega 2 minus omega 1 is equal to CS times omega, right? So I can write this equation as E E2 minus E1 equal to I over 2, and instead of omega 2 minus omega 1, I will write CS omega. Sorry. This is omega. This is not omega 2. This is omega, right? Cs times omega times omega 2 plus omega 1, right? So omega 2 plus omega 1, and we also know that omega is equal to omega 1 plus omega 2 divided by 2. Therefore omega 1 plus omega 2 is 2 times omega, so I can write 2 times omega over here. So what does this become is that E2 minus E1 is equal to, okay, this 2 is going to cancel with this 2. I'll have I, this I, and Cs omega square. Okay? So this is my equation now, that E2 is equal, E2 minus E1 is equal to Csi omega square. Now let's look at this. Acha ji. Now, what does this mean? What does this mean? And what does this equation mean at all? Okay, if I am planning to have some variation in energy, I can go ahead and calculate the mass of a flywheel that I'm going to use. Okay, E2 minus E1 is equal to Cs I times omega square. Okay. Now what is I? I is equal to E2 minus E1 divided by Cs times omega square. Okay. So I can go ahead and find the mass of the flywheel from this equation, that what kind of flywheel am I going to use in order to to work with the energy variation that I have in this case. Okay. So this is how we would design a flywheel for a certain range of energy fluctuation. If you look at this problem, this is about the flywheel that we just discussed. It says that in table table 16-6, list values of torque used to plot figure 16-28. The nominal speed of the engine is 250, so you have the speed of the engine in radians per second. And what it says that it says integrate the torque displacement function for one cycle and find the energy that can be delivered to a load during the cycle. Okay, determine the mean torque, um, and that is C figure 16-28, which we just saw when we were discussing the flywheel. Anyways, we are going to have a look at it again. It says that the greatest energy fluctuation is approximately between theta is equal to 15 degrees and theta is equal to 150 degrees of the torque diagram. And note that theta naught is equal to minus Tm using the coefficient of speed fluctuation. Cs is equal to 0.1. Find the suitable value for the flywheel inertia. ठीक है जी, so we have to find the inertia, find omega 2 and omega 1. ठीक है जी, let's have a look at the table. So this is the table, and that this table lists the torque after every 15 degrees of displacement. So for initially the torque is 0, at 15 degree it is 2800 pound, inch at 30 degrees, 20, 90, 45. So this is with an increment of 15 degrees. And it lists all these um, values, right? So basically you can go ahead and find the mean of these at the interval um, of 15 degrees, since we have what does it say, that the nominal speed of the engine is 250, and if we divide the for one complete um, let's see over here, and it goes up to 720. So if we add up all these intervals, the n is equal to 48, and therefore your delta theta is 4 pi divided by 48. That is so if you go ahead and numerically integrate the data, your E turns out to be 3368 inch pound. And this is the energy that can be delivered to the load. Now, if we look over here, it says that TM. So what will be the average, or what will be TM? That is going to be 3368, the one that can be delivered, divided by 4 pi, and that comes out to be 268 pound force inch, right? We can also go ahead and find our find our I, right? Um, with using our equation 16-64, it is just right, and that is going to be 0.565 pound force inch second square. Similarly, if you want to find out omega 2 and omega 1, we can go ahead and do that. Since we have our CS equal to omega 2 minus omega 1 divided by omega. So from this, we can go ahead and find our omega. 2 and or omega 1 from the relationship where your omega 1 is equal to 2 omega minus omega 2. So putting these values, you can get the value of omega 2 and omega 1. I think this is going to be it for the clutches, brakes, and flywheel. I'm not going to go any further, and you are going to and this is going to be enough for this for these topics. Thank you very much.